Hello and thanks for joining me. In this section we're going to be looking at phase and line voltages in three-phase circuits. Now I'm sure this is something that most of you know about or maybe even can remember, but if not, this will act as a refresher. Now, by this stage in your life you should all be familiar with a diagram like this. What it is showing is a three-phase sinusoidal waveform. Now it's probably bread and butter to you, but just as a quick recap, this chart here is showing us one complete cycle. Okay, so from 0 to 360 degrees. We tend to measure the position of a phase in degrees. Okay, so then one complete cycle, take for example the black phase here, phase 1. One complete cycle, it will go from 0 volts, it will reach its maximum voltage at 90 degrees, then it will go back to 0 and cross the 0 point at 180 degrees, then it will reach its minimum at 270 degrees and go back to 0 at 360 degrees. It will then continue to do the same thing again. On this chart, the maximum is 1 volt, but the maximum might be 300 volts, it might be 600 volts, it might be 1,000 volts, it might be 10,000 volts. It all depends on what voltage you're dealing with. When the black phase here is at its maximum, you'll notice that the blue and the red phases are at their crossing point, but they're both much lower than the black phase. In fact, they're the opposite, and they're just around half a volt in the opposite direction. So at this point, the potential difference between the black phase, phase 1, and either the red or the blue phases, phase 2, at this point, at 90 degrees, that potential difference is going to be 1.5 on this chart. However, at the next point, here for example, let's take 180 degrees, you'll notice that the potential difference between the black and the blue phases and the potential difference between the black and the red phases has changed. And now what is it? Approximately 0.7 of a volts. So it's constantly changing, and it changes every time we have a cycle, and that's how three-phase works. So when we talk about the specification of three-phase, we usually give it a voltage, for example 440 volts, and we give it a frequency which is say 50 Hertz in the UK, or maybe 60 in America, or if you work on aircraft it might be 400 Hertz. UK, USA aircraft. And these can vary depending on what the purpose is. So although this chart is showing us a 360 degree period, that 360 degree period is happening 50 times or 60 times or 400 times a second. And this represents just a snapshot of it. So we know that on a three-phase system we've got 3 wires, each wire is carrying a phase, and each phase is 120 degrees out from its neighbour. Okay. Now, this is bread and butter stuff to you, and you know this. So, you'll also be familiar with the concept of star and delta layouts. So, if I zoom out a bit, here we see a star layout. Now, again, this is probably something that you're quite familiar with, but just as a recap, a star-connected load is where the 3 line conductors are each connected to a load, and the outlets from the loads are joined together at N to form what is termed the neutral point, or the star point. And it's called that because it looks like a star. So if I have my 3 loads here, which I'll just shade in, I've called them Z for impedance. Remember, impedance is both inductance, capacitance and resistance. So I have my 3 loads. I've called them ZR, ZS and ZT. So in this case I've called my phases R, S and T. Now that's just a convention that I use. You could call them red, green and blue, you could call them 1, 2 and 3, anything like that, but here I've used R, S and T. So we'll see that load R is actually between phase R and the neutral point, and then load Z is between phase Z load S is between phase S and a neutral point, and load T is between phase T and a neutral point. And you'll see I've written here line voltage and phase voltage. Well, what does that mean? Well, line voltage is what I showed you on the chart above. Line voltage here is the voltage between any phase and any other phase that you choose at that point. So between, for example, the line voltage here is between phase R and phase S. So if I take those two wires and put a multimeter across them, what will the voltage be? The phase voltage is between R, for example, and a neutral line. So the phase voltage is always going to be lower than the line voltage. When we specify a voltage, say 440 volts, two things. One, that's the root mean square value. So it's effectively the average voltage, because don't forget the voltage is constantly changing in a sinusoidal form. So if we flip that voltage up, we get the RMS, which is approximately there. So although it's completely changing all the time, we refer to it by 440 volts RMS. So it's going to be the line voltage. It's going to be the voltage between any two phases. The phase voltage is the voltage that is going through that phase. So because these phases are connected at a neutral point, the phase voltage is going to be the voltage between the phase and neutral, which is obviously going to be lower. Now, as well as voltage in a circuit, we also have current. And just like we have phase voltage and line voltage, we also have phase current and line current. If I put a clamp meter on phase R here, and I measure the current flowing in it, it's going to be a certain value that I'm going to call I for current. Remember, I is always used for current. Line, IL. That is going to be exactly the same as the current flowing through the actual load on a star-connected circuit, even though the current flowing through the actual load is technically the phase current. So I'm going to call that the phase current. But IL and IP are going to be the same on a star circuit, because there's no other place for that current to come through. It gets to the load, it's got to go through the load to get out of it. But the line voltage and the phase voltage will be different. The situation's the opposite on a delta system. On a delta system, we still have our three phases, and we have, for example, here we have the line voltage, because it's between R and S. Now, the phase voltage is just a mathematical entity on a delta circuit. It doesn't do anything, so we don't need to worry about it. Because what happens is when the phase gets to the node here, it splits, and some of it goes one way and some of it goes the other way. So it stands to reason that the line current, which is the current flowing in that particular piece of wire, if I measure that, it's going to be different than the phase current, because the phase current is split between two loads here at this node. The line current is of less significance. So, on a star circuit, the voltage across the load is the phase voltage, and on a delta circuit, the voltage across the load is the line voltage. We know that the line voltage is going to be much higher than the phase voltage, because from our chart we know that the line voltage is the voltage between any two phases, which, for example, at 90 degrees is going to be 1.5, rather than the phase voltage, which is the distance between any phase and neutral, which on this graph is going to be a maximum of 1. So, as it's clear that the voltage and current through each load is different for star and delta circuits, how do we calculate the line and phase voltage and current if we have one and not the other? I am now going to show you. On this chart, I have phase voltage. Okay, what I've done is I have plotted three phases on a diagram, and each phase in this instance is 220 volts. So the phase voltage of red and the phase voltage of S and the phase voltage of T is 220 volts. And I'm going to show you how to connect the line voltage. Generally, as I said, voltage is specified by line voltage, but to make this clear how we get there, I'm starting with phase voltage and going back to line voltage rather than the other way. I've drawn this to scale, so these angles, 120 degrees, are correct. So what I can do is I can do this graphically. If I bring my ruler up, for example, I can, if I specify a different colour, and I think we'll choose green because it's a nice colour. If I link these two phases here with my green pen, the distance between this point and this point is going to be the magnitude of VL. So the magnitude of VL equals distance between two points. I could do it between VT and VS as well, or VR and VT. It doesn't matter. Although the voltage is a vector, when we're specifying it here, we're only interested in its magnitude, not its direction. So I could use trigonometry to work this out, couldn't I? That's not going to be too difficult. Or I could just put my ruler, because I've drawn this to scale, and I could measure the length of this green line, and that would tell me what VL is. Or I can use standard vector analysis methods, graphical vector analysis methods in this case, to work out what it actually is. So let's do that. What I do, and you'll notice, I'm going to copy the VS line up here, and I'll make sure its magnitude is the same, because I have got this circle here to guide me. So if I then do that twice, I do it once from there, and then I do it once from here, and this again is something you'll probably be familiar with. Now I think I've got the length the same there. And then if I then copy VR, so the red line up here, and I draw that line across, all these should meet, so I'll just have to increase the length of that other line, pardon me. Why is that not spinning? Oh, heavens above. Oh, this is most annoying, isn't it? Okay. So we'll bring that back to 60 degrees, we'll pop that there, and we will connect that. Right. What I now have here is a parallelogram. All I've done is I've copied the vector VS from down here up to here twice, and then I've copied the vector VR as well. If and I pick a different colour now, let's go for purple, if I then connect the two corners of that parallelogram, you will be unsurprised to learn that the length of that line is also VL. Okay, you say, well, that's of no use to me at all. How does that help me work out the magnitude of VL? Well, you know this by now. I shouldn't really have to teach you, but I'll indulge you because I get paid. So if we go around here and we connect these two lines together with another purple line, apart from the fact that we are now making a beautiful set of triangles, what we can say here is that this angle here must be 30 degrees. And this angle here must be 30 degrees. And we know the value of VS and we know the value of VR. Therefore, we can say that the line voltage is going to have a value, and the value will be line voltage is going to be 2 multiplied by the cosine of 30 degrees multiplied by the phase voltage. Why? Because the hypotenuse, which is in this case the phase voltage, is 30 degrees away from the base, and we know that cosine or in this case the cosine of 30, is the base over the hypotenuse, which is the base over the phase voltage. If I put cos 30 into my calculator, it will tell me something interesting. It will tell me that it is the square root of 3 divided by 2. So if I then alter this, I now go VL for line voltage is going to be 2 multiplied by the square root of 3 divided by 2 multiplied by the phase voltage. Well, that's interesting, because the phase voltage we know, and we can cancel these 2's out. So VL equals root of 3 multiplied by VP. I keep writing VR there, don't I? That's not very good of me. Let's make that VP. If VP equals 220, then VL is going to be root 3 multiplied by 220, which is 380 volts. And as you'll know, a standard voltage that we often see in the UK is given as 380 volts. So what that means is that a three-phase system with a line voltage of 380 volts will be made up of 3 phases, each of which has a phase voltage of 220 volts. What voltage do you have in your house in the UK? 220 volts, single phase. How do you think we get that? It's quite simple. We take it off a star system from a 3-phase supply. That is why your house is 220 volts, and that is why industry is 380 volts, 3-phase. So I hope that that has cleared up the difference between phase voltage and line voltage. The way that we calculate phase current and line current is exactly the same, and for the rest of this course we'll be using the root of 3 a lot. Thank you very much for your attention, and have a wonderful day.